All right, number one. The following list of test scores has an average of 50 and an SD of 10. Use the normal approximation to estimate the number of scores within 1.25 SDs. So we have a center of 50, and our SD is 10. This problem is actually really easy, but you might have misunderstood what the question was asking. It's saying if we go out to plus 1.25 SDs and minus 1.25, how many scores did we actually catch? Well, how far out do you have to go if you want to go 1.25 SDs? Well, if your Z is 1.25 and you times that by your SD of 10, I get 12.5, which would put me at 62.5 and 37.5. Okay, so we count that up. How many of those scores are actually between 37.5 and 62.5? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 36 is out. 11, 12, 64 is out. 29 is out. 13, 14, 15, 16, 17, 18, 72 is out. 19. I got 20. Did I count that right? And how many are there total? So 20 out of, wow, that's pretty cool. Okay. Well, until my smartboard comes back on, I don't know what we're going to do. So 20 out of 25. Oh, did I do this backwards? Okay, sorry, I did B first. That was backwards. So there are actually 20 out of 25. And if we use the normal approximation of data, what will we get? Well, I just need to look up 1.25 on the yellow sheet, and we get 77 point, or 78.1. Some of you aren't paying attention. 78.1, and we actually had 75. What's 20 out of 25? It's not 75. 70. What's 20 divided by 25? 80%. So the normal curve tells us we should capture 78%, and we actually captured 80%, which is pretty close. It doesn't matter. I mean, it describes the same thing. So you you could answer that either way. It doesn't really matter. Okay. Well, I'm without a smartboard, but I'll keep going. Well, I can. Okay. So 2. You're looking at a computer printout of 100 test scores, which have been... Oh, we didn't do 2. Sorry, we're going to 3. From the mid-1960s to the early 1990s, there was a slow but steady decline in SAT scores. Oh my goodness, people got dumber. For example, take in the verbal SAT. The average in 1967 was about 543. By 1994, the average was down to about 490. However, the SD stayed close to 110. The drop in averages has a large effect on the tails of a distribution. So A, estimate the percentage of students scoring over 700 in 1960, and then estimate the percentage of students scoring over 700 in 94. If that light for the smartboard turns back on, let me know. So we basically have 2 different curves that we're going to look at. One of them is centered at 543, and the other one is centered at 499. And they both have an SD of 110. Okay, so I want to know how many people in the first one were right of 700, and how many people in the second one were right of 700. So I need to find the z-score in the first one, 700 minus 543 is 5157, and we divide that by 110, and I get z equals 1.42. Okay, on the other one, I'm going to do the same thing, and I get 201 divided by 110, and I get z equals 1.8. And then we do shade norm from 1.42 to 5. What did you get there? 19%. That's close enough. And then if I do shade norm from 1.8 to 5, 17%. So you guys got, I don't have a calculator. No? What'd you get? That sounds better to me, 7.8. Okay. That sounds better. Oh. Oh, sorry. The first one was 7.8 and the second one was 3.4. Okay. Sorry. I don't have a calculator at the moment. I don't even know if this is recording. Okay. That's true. Okay, 4. Um, on the math SAT, men have a distinct edge. In 2005, for instance, the men averaged 538 and the women averaged 504. Estimate the percentage of men getting over 700 on this test, and then women 700. So I'm actually going to use this calculator. It's basically the exact same story, but now instead of 543 and 499, it's going to be 538 and 504. So 538 and 504. So the first one has a difference of 162 divided by 110. Oh, it's 120 this time. Sorry, 120. So 162 divided by 120 is 1.35. And I'm going to do my shade norm from, what did I say it was? 1.39, 1.35 to 5. And I get 8.8%. Okay. And then on the next one, I'm going to do 700 minus 504 and divide that by 120. And I get 1.63. So shade norm, 1.63 to 5. And I get, oops, it didn't work. 5.1. Okay, are we getting the hang of this? Kind of? It's coming up. Okay, what's the next one? 5? All right, some of you still are you confused? Do you need more help? Do you guys get what you're doing? Okay. All right, number 5. We're getting a smartboard back. In Haynes 5, the men aged 18 and over had an average height of 69 inches and an SD of 3. The histogram is shown below with a normal curve. The percentage of men with heights between 66 and 72 is exactly equal to the area between A and B under the blank. So it's going to be between -1 and +1 under the normal curve. Does that make sense? So I almost wrote on the smartboard with that. Hey, we kept recording. So I have this. So we have this histogram of people, and then we estimate it using the normal curve. Okay? And is the normal curve going to be perfect? No, not at all. Cedar, are you talking about this? Then you better stop. So if we go from 66 to 72, and that happens to match up exactly with -1 and 1, then the areas should be the same. So under the, it should be, sorry, is exactly equal to the area between -1 and +1 under the histogram. And then it's -1 and +1, but it's under the histogram. And then the second one would be -1 and +1 under the normal curve. Oh, sorry, I said that wrong. Yeah. So it should be inches, inches, and histogram, and -1 and +1 normal curve. So I I read that wrong. I'm sorry. So if we add up the actual boxes, oh no, you don't. So the true area is exactly equal to the boxes, but it's approximately equal to the normal curve. So I misunderstood that question when I read it. Okay. Oh, don't erase it. You're fine. Oh. Okay, did we skip 6? Yes, we skipped 6. 7. Among freshmen at a certain university, scores on the math SAT follow the normal curve with an average of 550 and an ST of 100. Fill in the blank and explain briefly. A student who scored 400 on the math SAT was at the blank percentile. So, we draw our normal curve. Our average is 550 and our ST is 100. So we want to mark somebody at 400, and we want to know their percentile. Percentile measures area to the left. So we want this area over here. Okay? So I need to do 400 minus 500. Why did I do it in that order? Oh, 550. I do it in that order because I want my sign to be correct, and in this, we want it to be negative. So I get -150, and I divide that by 100, and I get -1.5. What does -150 tell me about this score? It's 150 points below or to the left from the average. Okay. What does -1.5 tell me? That's how many SDs I am below the average. And I actually like using my hand calculator. It's way faster. So I'm going to shade norm. What do I pick for my left bound? You can either leave it or put in -5. And then -1.5. And then I draw. And I get 6.7%. So you guys got? Whatever. Okay. All right. And for B we're going to go backwards. To be at the 75th percentile, a student needed to score what? Well, where is the 75th percentile? It's to the right. So we make a mark, and we say that area is equal to 0.75. Okay? But 0.75 describes all of this. And I don't have any way in the calculator, at least I don't know any way in the calculator to look this up. So what we have to do is calculate the area to the right. How much is to the right? 25%. And how does that help us? If we put 25% on the other side, then that gives me 50% in the center, and I have a table that will tell me 50% in the center, and it would be 0.66, 0.67, somewhere in there, 0.67. And what do I do with that 0.67? This is 0.67 SDs, but I don't want to know SDs. I want it to be an SAT score. So I multiply it by 100, and then I get 67. What does 67 tell us? That's how many points higher than the average this person was. So I add that back to 550, and I get 620. Oh, no, that's 67, sorry. 617, yeah. So this one's kind of weird because it's the same number, but this is how many SDs we were above. So I convert SDs back into points. And then I know that I am 67 points to the right from the average. So I did 550 plus 67, and I got 617. Yep. Okay, and really, that question, A and B together, that's essentially the whole class. That's what statistics is. Now, we're going to be using this in lots of different types of contexts, but that's the heart and soul of the class. If you can take a score and create a percentile, or take a percentile and create a score, you can do this class. All right, and number 8. Okay, true or false, and explain. If you add 7 to every interest on a list, that adds 7 to the average. True. Okay, and that's, so let's take our regular normal curve, and then here is my copy normal curve. What happens when I add 7? Everything shifts to the right 7. Okay? If you add 7 to every entry on the list, that adds 7 to the SD. False, because the red graph and the blue graph have exactly the same spread. And SD is a measure of spread. So B is false. C, if you double every entry on a list, that doubles the average. So what would doubling do to this blue graph? It would be twice as long, so now it's going to go clear out to here, and it's going to be half as tall. So it's going to look like this. Right? Did that double the average? Yes. The average went from here to here. Okay? And D, if you double every entry on a list, that doubles the SD. True. Because is the green graph more spread out than the blue graph? Yes, and SD is a measure of spread. Okay, if you change the sign of every entry on a list, that changes the sign of the average. Yes. So, for instance, let's say we had a histogram that measured how much money you earned or spent yesterday. Some of you earned money and you didn't spend any of it, or you spent some of it, and some of you spent money but you didn't earn it. So some of us might have positive numbers and some might have negative numbers. If the average money gained yesterday among all class members was $28, that means you take the positives and the negatives, you combine them together, and you divide them by the number of students, we end up with 28. Okay? If the average ended up being -5, what does that mean? On average, we spent more than we made. But what if my average was 28 and I changed everybody's sign from positive to negative or negative to positive? What would the new average be? -28. So for E, if you change the sign of each entry on a list, that changes the sign of the average. True. If you change the sign of every entry on a list, that changes the sign of the SD. False. Why? SD is always positive, every time. And then we need to do 9. One more. Well, right after the 8. It's on the board. Okay, number 9. You're having a bad day. You need to. Where's the do-over button? No, it's a 9. Okay. The median, the median and average of any list are always close together. False. If the graph is normal, then they're always close together, but they can be way off. B, half of a list is always below average. False. Okay. C, with a large representative sample, the histogram is bound to follow the normal curve quite closely. False. Well, so the more data we have, the more accurate the histogram is going to be. But what if the data itself is not normal? For instance, income. If you were to graph income, you always have a big hump at the beginning and then a long tail. And talking to more people isn't going to change that, because some people are filthy rich, but most of us are somewhere on that left side. Yes. Yes. Okay. And D, if two lists of numbers have exactly the same average of 50 and the same SD of 10, then the percentile of entries between 40 and 60 must be exactly the same for both lists. Ooh, that one's exactly the same SD and exactly the same. I I think it's true. So the percentage of entries between 40 and 60 must. I think the word exactly makes it false. Yeah.